All right, this is the lecture to start off talking about biochemistry, or the chemical level of organization. So we know that living things are organized from chemicals working together to make cells, cells making tissues, tissues making organs, and so on. So it's important for us to take a look at this very basic level, this chemical level of organization. Remember that in biology, structure determines function. So depending upon how your those molecules are shaped and assembled, that determines what they are able to do. And so we need to have an understanding of some of the structure and main organic molecules that living things utilize. So starting at the beginning, an atom. An atom is anything that has, an atom is a single unit of a material, simplest unit of matter, not of life. The cell is the basic unit of life, an atom is the simplest unit of matter. Matter is anything that has mass and takes up space. So anything that's anything is made of matter. And so we've got different flavors of matter, and those are the elements. The different kinds of matter that we have are the element, like the periodic table of the elements, hydrogen, helium, lithium, beryllium, boron, carbon, and so forth. That is all the different types of matter we have. The type of matter is determined by what type of atom you have. And so you've had this many, many times before. Basic atomic structure, if we're talking about hydrogen, we would have number 1 on the periodic table. You would have 1 positive proton in the nucleus and an electron in the electron cloud. So this region is the nucleus, this is the electron cloud. Keep in mind that we draw atoms in a certain way, but they're not really that way. This is just a graphical representation of that atom. In reality, this nucleus would be, if you're taking like a football stadium, that nucleus would be very, very, very small. And somewhere out in the track area around that atom would be some electrons. They don't go in these nice orbits. This is a way of drawing it that is a good representation, but it's really not like that. But it works for us and it explains some things. Okay? So if we change this or make another model of, let's say, carbon, number 6 on the periodic table, we have the atomic symbol C, and we'll draw our 6 protons. That would make up our nucleus. And because carbon's atomic mass is typically either 12 or 14, we would be able to go ahead and look at the total atomic mass would, even though this has 6 protons because carbon is number 6, and this has 1 proton because hydrogen always only has 1 proton, we still can look at our total atomic mass, which in this case would be, carbon would be 14. We'd have 8 neutrons to make up the rest of that mass. And so let's put 8 neutrons. Now I'm going to put a little slash through those to represent the charge. Neutrons have no charge. Then we still have, out here in our electron cloud, we still have our negative electrons. So let's put our electrons out here. 1, 2, 3, 4, 5, 6. So a total of 8 electrons. Typically, you will have the same number of protons as electrons, positive protons, negative electrons, and a normal atom should be balanced and not be positive or negative. If it has more or less electrons than protons, you will have a charge, and then you'll be known as an ion or a charged particle. Okay? So if we could take our hydrogen, for example, let's say that we have 1 proton, so that's a +1 charge, and we have 1 electron, which is a -1 charge. Our total overall charge for this is 0. neither of these are ionized right now. They are not a charged atom. But you can have be charged. You cannot do that by gaining or adding protons. Protons are set in the nucleus. You don't separate protons unless you're undergoing a nuclear reaction. There's no nuclear reaction here. So how can we make this have a charge? Two options. We can either get rid of that electron and just have a proton, and then overall you would have a +1 charge. And that means this would be ionized. It would be a charged particle. Because it's a positive ion, it will be known as a cation. If it's a negative ion, we call it an anion. Oops. In both cases, you can see that word ion is part of that. Okay? We could, instead of taking away that electron, let's add another electron here. And now all of a sudden, we've got a 9 - 2, and our overall charge would be -1. It's charged. This is now an ion, whereas this is a neutral atom. So one thing to look at when you're looking at atoms is, do they hold a charge or not? Do you have the same number of protons as electrons? If you vary in the number of electrons versus protons, you will be holding a charge, and then you'll behave a little bit differently because you have become ionized. So, collectively, the subatomic particles that we have for this atom are protons, neutrons, electrons. Protons determine which element it is. Neutrons make up the rest of the mass of the nucleus, and electrons are out here in the electron cloud, and they influence whether you are ionized or not. Electrons also are going to determine your reactivity, and we'll talk about that in a minute. Going back to the periodic table. So the periodic table shows all the different elements that are possible for us to make something out of. Living things primarily use nitrogen, oxygen, carbon, and hydrogen, and a little bit of sulfur and phosphorus thrown in there. But those four, particularly those four elements, carbon, nitrogen, oxygen, and which one am I forgetting? Carbon, hydrogen. Those four are used to build the most molecules in living things. We're mainly made out of just those four elements. All right. Okay. So when you're looking at those particular elements like hydrogen or carbon, and also nitrogen and oxygen, what makes them so useful for living things to build things out of them? Why aren't we built out of other things, like a lot of the metals? We only need small amounts of those. Why do we use so much of these other things? Well, it has to do with the electrons. To explain this, we'll have to back up a step. From now on, I'm just going to maybe draw a symbol for the nucleus, because we aren't going to really worry much about neutrons and protons right now. So let's say we're looking at carbon. Okay, so I'm just make a big C, and that's going to act as our nucleus. We know that carbon is 6 on the periodic table, so it does have 6 protons, so we should have 6 neutrons, or excuse me, 6 electrons in an unionized atom. So to do this, I'm going to start to draw these rings around here like you saw before and fill these in. These represent energy levels or shells. Okay, this is not really like this. In the real world, okay, electrons are not in these nice little orbits like planets around the sun. They're somewhere around this in these layers, but we aren't sure exactly where, and they get really complex pathways in them. And so we just refer to these as energy levels or shells that these electrons can fill. Electrons like to be paired up as well. So because these are paired here, this first energy level or shell the first energy level or shell, I'll catch up with you in a moment, will only be able to hold 2 electrons. And then it's full. And then we have to move up to the next energy level. This energy level can hold 8 electrons. and then it's full. So why is carbon so, like in particular, so useful for living things? Well, this outermost energy level, whether it's this second one in carbon, or if we draw hydrogen again and that energy level right here that just has the 1 in it, this outermost layer is called the valence level. The outer level or layer is the valence level of that atom. That is the most important layer as far as we're concerned in chemistry, because that layer, and whether you have an unpaired electron, if you can hold more electrons, that influences how reactive you are, who you're going to react with, and in what quantity. For example, we could say that we could look at the periodic table and some things are really super reactive, like fluorine or chlorine. Fluorine gas is really toxic. If you inhale it, it's going to react with your lungs and kill you, and it's going to be a really bad day. So why is it so reactive? It's because it wants one more electron. It's got one unpaired electron in this valence level. And it totally wants to react with something to steal, usually, an electron from something else. And that will mess you up, right? On the other hand, right next to that is argon on the periodic table. Argon is very, very, very similar to fluorine, but it will totally never hurt you because it has a full valence level. Therefore, it doesn't want to react with anyone else because it doesn't want to give away an electron or get an electron or share electrons. It's perfectly content. So whenever you have a stable outer valence level, you're not inert, but you're stable. You're not going to react. You're full. Okay? So that's what guides the reaction. With that in mind, with this valence level for carbon especially, because it has 4 unpaired electrons in its valence level, it can hook to a lot of things, which means it's really useful for living things, to build big molecules out of. That's why the valence level is so important. We already talked about ions being a difference between the number of electrons and protons and then creating a charge. You can have another variation on any atom called an isotope. So in an isotope, you have the same atom, like hydrogen. Hydrogen always has 1 proton. But let's say we have what's called hydrogen 1, or H1. It has 1 proton and 1 electron. So it behaves a certain way chemically because of this electron. It doesn't have any neutrons. Hydrogen 2, that number 2 is referring to the atomic mass. You have 1 proton and 1 neutron. And you have 1 electron. Same as before. And then you can also have hydrogen 3, which is tritium, 1 proton, 2 neutrons, and 1 electron. These different variations of this hydrogen are called isotopes. Chemically, they behave the same because they have that 1 electron. From a perspective of which atom they all have 1 proton, they're hydrogen. But they differ in their masses, okay, the neutrons, right? If you get too many or too few neutrons, then you can have an unstable nucleus and you end up looking at some sort of radioactivity like radioactive decay. So some isotopes are totally safe, we use them all the time. Other isotopes are used in like medical imaging, or they're radioactive and they can harm you. So it just depends on which isotope of a particular element you're looking at. All right, we will stop there and we'll pick up more with chemical compounds next time.